Hi everyone, welcome to the last webinar of the Diabatix summer series. In today's talk, we will be talking about applying boundary conditions. Boundary conditions are important and will need to be set in order to solve both ordinary and partial differential equations. A bad choice of boundary conditions can have great impact on the results and may lead to divergence of the solution or even just a bad solution. So today we will learn how to set them properly. I am Ine. I'm an R&D engineer at Diabatix. That means that I'm directly involved in developing the code, and I will guide you through this talk today. There are 4 webinars in the summer series, and in the previous webinars, my colleagues Gert-Jan and Reshma already talked about CFD simulations for thermal engineers, how to efficiently post-process simulations, and how to design a cooling jacket. They briefly described which boundary conditions were used in their setups, but today we go a little bit deeper into them. But before we go into the why do we actually need boundary conditions, when we talk about boundary conditions, you often hear the terms Dirichlet, Neumann, or Robin, but what do they actually mean? When you have a Dirichlet type boundary condition, you have a type of boundary condition that specifies the value along the boundary. When you have a Neumann type boundary condition imposed on a differential equation, the value of the derivative is specified. And with a Robin type boundary, a linear combination of values and derivatives is imposed. So that's a little bit a background to the different terms. But maybe first, why do we actually need boundary conditions? In CFD software, the Navier-Stokes equations are solved. So if we just ignore the other variables for a moment, like the turbulence, the energy, we have a minimum of 4 equations that need to be solved. We have 3 momentum equations in the x, y, and z direction, and we have the continuity equation, which you can see here on this slide. And in these 4 equations, we have 4 unknown variables. So we have ux, uy, and uz, and we have the static pressure P. So we have 4 unknowns, so we have to specify boundary conditions for these unknown variables. I will go through the main boundary conditions which are available in the platform based on the case which was discussed during a previous summer series webinar by my colleague Gert-Jan. Let's, for example, take the cooling jacket case he used in the first webinar. I will quickly go through the setup first in the slides, and then we will switch to the platform to show you how to really apply them and what other options there are. So we have the cooling jacket case, so it's basically the thing which is placed over an electric motor. The electric motor itself is not simulated. The cooling jacket is made out of aluminum with these material properties. So a density of 2,700 kilograms per cube and a thermal conductivity of 103 watts per meter Kelvin. In red, you can see a first boundary, namely it's a wall boundary. So as I said before, the motor itself, it is not simulated, but it's simplified as a heated wall. And to that heated wall, we apply a heating power of 700 watts. Then in the fluid region, which is shown here in blue, we have an inlet at which we specify the temperature at which the water enters the domain, and the flow rate, which is set to 3.8 liters per minute. On the other side, we have the outlet. So let's switch to the platform. I went ahead and opened it already. So let's go to the project folder summer series, where we can find all the previous cases. And let's make a copy of one of those so we can modify it and really show the different boundary conditions. This can be done by clicking on the duplicate button. and given a new name for the new case. Then you can click on Start Setup and we can start looking at boundary conditions. So first, let's start with the fluid region. I will make the solid invisible for a moment so we can really see the fluid region. And then if you click on the fluid region, you see the different boundaries. So here we have an inlet and an outlet boundary condition, and you can also make them visible separately by clicking on the little eye symbol. So these boundaries, they were already present in the original step file we used to create the case. And then they are automatically recognized and the inlet and outlet surfaces are shown as boundaries. If this would not be the case, or you would like to add another additional boundary or replace one of the existing ones, you can simply click on the region and then click on the Add Boundary button at the bottom. The only thing you have to do then is give it a new name and select the step file which you can upload. After creating the boundary patches, we can assign a specific type and specific properties to them on the right hand side of the screen. If we click, for example, on the fluid inlet, we see that it's now defined as a fixed flow rate inlet, but there are also several other options like a pressure inlet, a pump inlet, a fan inlet, and we will talk about that more later. For the outlet, for example, we have a pressure outlet option. So I would like to start with focusing on the inlet and outlet boundary conditions. So let's switch back to slides for a moment. In fluid type problems, except for buoyancy-driven flows, there must be an inlet and an outlet, which defines how the fluid enters and leaves the domain. There are different kinds of inlet conditions. Think, for example, of velocity inlets, pressure inlets, and some kind of variation, the fan and pump inlets. You're probably most familiar with the velocity inlet boundary conditions, as they are the ones which are the most used in CFD codes. They are used when the speed or the flow rate at which the fluid enters the domain is known. In the platform, a velocity inlet type boundary condition is denoted as a fixed flow rate inlet. And in this boundary condition, we specify a value normal to the boundary patch. We can either specify a velocity value, which you can do if your velocity at which the fluid enters the domain is known, or a mass or volumetric flow rate. And this is often used when the flow rate is a known parameter, or if you want to calculate, for example, the pressure drop throughout the system. So in the platform itself, you have several entries. You have the temperature, then you have U, m dot, or q dot, which are respectively a velocity, a mass flow rate, and a volumetric flow rate. The fixed flow rate inlet boundary is often combined with a pressure outlet boundary, which is also the case for the cooling jacket as we have seen on the platform before. And with the pressure outlet condition, you basically specify the total pressure at the outlet. So when you have, for example, an isothermal simulation and the inlet and outlet boundary condition are set, the CFD code will be able to solve for the flow field in the entire domain. But what if you have a case where you don't have the velocity at which the fluid enters or the flow rate available? You can't use the fixed flow rate inlet, but still boundary conditions need to be set for the velocity components and the static pressure. Pressure inlets are typically used in buoyancy-driven flow problems. So for example, if you would like to simulate a room with a heat source in it somewhere, an outlet, a chimney for example, and a window from which cool air is drawn in and which acts like an inlet, but you don't know at which speed the air will be drawn in, so you can't use a fixed flow rate inlet. In this case, we would use a pressure inlet. But how does a pressure inlet work? You could think that it would just be by specifying the static pressure, as we need a boundary condition for this variable. But if we would set a static pressure, we would get an unstable problem. And this can be easily seen from this equation. If we set the pressure gradient by setting static pressures at the inlet and the outlet, for example, so we set the gradient of the static pressure, and the velocity field we compute by solving the Navier-Stokes equations has to match this gradient field exactly. Small errors in this field will quickly lead the solution to diverge. The solution to this problem is to set the total pressure at the inlet instead of the static pressure. The total pressure is related to the static pressure by the equation of Bernoulli. So how does it work in the software? Because we only solve for the static pressure and not for the total pressure. So the user specifies the total pressure at the boundary. Then in the CFD code, the static pressure from the previous iteration is used to calculate the velocity, and which can be derived from this formula. Then the velocity is applied at the inlet as a boundary condition. The CFD equations are solved again to update the static pressure, and then we proceed to the next iteration. So basically, a pressure inlet works very similar to a fixed flow rate inlet, but while for a fixed flow rate inlet the velocities are kept constant every iteration, for a pressure inlet the velocity varies at each iteration. Pressure inlets are typically used in combination with pressure outlets. In a fan or a pump inlet, the static pressure is set based on the total pressure, which is specified, and the pressure drop, which is also specified as a function of the volumetric flow rate across the patch. The pressure drop in function of flow rate is called the fan or the pump curve and is specified in the libraries. For the pressure outlet, it was already discussed, so this boundary condition defines also the total pressure at the outlet boundary in our software, and the total pressure is assumed to be constant over the outlet. So in summary, a velocity inlet, then the velocity is specified, the pressure is calculated. For a pressure inlet, the total pressure is specified and the velocity is calculated. And the same for a pressure outlet. So the total pressure is specified and the velocity is calculated as well. Besides inlet and outlet boundary conditions, walls are also important to talk about. So walls, if you want to store liquids or contain gases, you need walls, and in our software we only use impermeable walls, so this means there is no flow through the wall. At walls, a no-slip condition is automatically applied by our software, and this means that the tangential velocity of the fluid at the wall is the same as the fluid velocity. So the fluid will have zero velocity relative to the boundary. The normal velocity component is set to be zero. A boundary layer will develop in a no-slip boundary condition. And to use one of the terms before, this kind of boundary condition is a Dirichlet type boundary condition. The main function of our software is to do thermal simulations. So that means that in addition to the momentum and the continuity equation that we already discussed, also the energy equation is solved. So we need additional boundary conditions to create a well-defined system. And typically used wall boundary conditions are the following: a fixed temperature wall, a heated wall, an external wall, or insulated walls. So let's take a look at the platform again. So in the solid region, we also have a predefined boundary, which we can quickly visualize. So this is the solid, and inside we have defined a boundary, which you can see here. In the original cooling jacket case, it is set up to be a heated wall. So as I explained before, this boundary is in real life connected to the motor, but we don't simulate that one, but we know the motor has a heat output of 700 watts, so we can use a heated wall instead. And what we actually do is then apply a fixed heat flux boundary condition. Another option, if you want to specify a temperature at the wall boundary, you can use the fixed temperature wall. The only thing you need to do is to set the temperature, which you can see from the star, which is next to the T. And the fixed temperature wall boundary condition will impose a value at the boundary, so it's a Dirichlet type boundary condition. Another option you can choose is the external wall. It doesn't really make sense in this case to really apply it here, but I just want to show it to you. And with the external wall boundary condition, you specify a convective heat transfer boundary condition. So you will need to set H, which is the heat transfer coefficient, the temperature outside of your simulation domain, so the ambient temperature. And optionally, you can also set RD and RK, so which you will need to do if you have a thermal resistance layer at the wall. If nothing is specified for the boundaries, for example, for the outer surface in the cooling jacket solid, and it's not listed here, this means that it will be treated as insulated walls in our software. So this condition specifies zero heat flux condition, and insulated wall boundary conditions are of the Neumann type. So if you want to set the boundary condition, you have to upload the step file and assign properties to them. If nothing is specified for a boundary, an insulated wall type will be used. So thank you for listening to this webinar. I hope you enjoyed it and learned a little bit more from it. If there are any questions, please let me know and I will be happy to answer them. We already got one of them from Steven. He asked, what is the physical meaning of a total pressure and a static pressure? So pressure, it's a continuous physical force which is exerted on an object by something, a fluid or something like that. Let's just say the air around us and we sit inside a building. So the static pressure is the pressure you have if the fluid, the air in our case, is not moving or we are moving at the same speed as the air. The static air pressure is the same in all directions. Total pressure is the pressure which the fluid exerts when it's brought to a stop. So if you would stand outside, for example, and there's a severe wind, the total pressure is then what acts on you as you face the wind and the air collides with your body. So you really feel the wind pressing on your face. Dynamic pressure then is the pressure of a fluid that results from its motion, and it's the difference between the total pressure and the static pressure. I see we don't have much time left for any other questions, but you can still send me your questions regarding this webinar and I will make sure to contact you very soon to answer them. Thank you again and hope to see you for one of our next webinars.